Okay. Well, I've been wondering if my talk is the one that you least wanted to hear, but felt that you had to hear. I'm going to be talking, we just heard from the last speaker that sustainability is a megatrend. And I guess what my talk is really about is that the definition of sustainability is changing. And I'm going to be talking about the latest science, the latest report on what is the definition of a sustainable fishery for the kinds of fish that this group is most interested in, the oily little fish, which are the source of most of the omega-3 fatty acid products. So one of the things I've been doing, really focusing on the last few years, is chairing a task force called the Lenfest Forage Fish Task Force. And we just, in April of this year, released our report called Little Fish, Big Impact, Managing a Crucial Link in Ocean Food Webs. And I'm going to give you a brief overview of the process the task force undertook to come up with this report and also what our recommendations are. I'll also say that the full report is available on a website. You can download it, and it's free. Okay, so the Lenfest Forage Fish Task Force consisted of 13 preeminent scientists. They cover many different disciplines and came from many different countries around the world. And our objective was to develop consensus recommendations on how we should be managing what we call forage fish in a way that accounts for their important role in marine ecosystems. So the task force worked for 3 years, quite a long and in-depth project. We conducted workshops. We made site visits to some of the most important forage fish fisheries in the globe, including the Peruvian anchovy fishery. We took a look at forage fish fisheries around the world, the theory and the practice, to see what lessons we could draw from those about what's successful management and what wasn't so successful. And we also developed some new science and syntheses. And I'm going to describe some of that today. Okay, so what are forage fish? And you may be wondering, why do we call them forage fish? We call them forage fish because everything else in the ecosystem forages or feeds on them. And these are really crucial species in ocean food webs. They feed on tiny single-celled plankton, and so they are the main conduit for energy transfer from the base of the food web all the way up to the upper trophic levels. These fish are generally very small in body size. They often form large schools, and you generally live a pretty short life. They include things like sardines, anchovies, sand eels, krill, and herring. So as of now, our latest statistics say that about 37% of the world's wild marine fish catch consists of these little fish, forage fish. And in fact, the largest fishery in the entire world of any kind is the Peruvian anchovy fishery, which is a forage fish fishery. So these fisheries are very significant from a perspective of people looking at fisheries in general in the marine environment. 90% of the catch of forage fish is ground up into fish meal or reduced into fish oil and then used in various products, including aquaculture and the kinds of products we've been talking about here. Only 10% of these fish are used directly by humans for human consumption. These schooling small fish were the very fish that inspired the idea that the seas were so productive, vast, and limitless that nothing we could do could ever harm them. And this idea was with us for many, many centuries. The print that I'm showing here is from the 1500s, from the Baltic Sea, and it depicts the Baltic Sea herring population. And there were reputed to be so many of these herring that if you threw an axe into their midst, the axe would stand upright. So that was the thinking about how abundant these forage fish really were. But now we know better because we've actually seen that these fish not only can collapse, but that collapses have occurred. And these have occurred, a series of pretty famous collapses, if you're a fishery scientist anyway, have occurred. The California sardine fishery. Those of you who've been out to California, to Monterey, California, have you been to Cannery Row that John Steinbeck made famous? Used to be a place where everything was focused on canning lots and lots of sardines, and now it's a tourist attraction, and there's no fishing or processing there. The Peruvian anchovy fishery collapsed, spectacular collapse in the early 1970s. At that time, that's one species represented 10% of the world's fish catch. The Namibian sardine, Japanese sardines, all these species, very large volume fisheries, have shown collapses. Now, they also have shown that they can recover given a chance. So the task force, again, one of the things that we did, of the many things we did, was to look around the world and to see where we could draw lessons from examples of fisheries management of these types of fish. We looked at 9 different ecosystems in detail, and due to time constraints, I will only touch on a couple of these here. Again, during cocktail hour, or if you want to download the full report, or both, you can learn a lot more about each of these. So one I'd like to speak about is the Barents Sea. And this is a sea that is north of Norway. It's a place where we found that there is in place an effective management regime for the forage fish there, which is called capelin. And the effectiveness that is in place now kind of came about as a result of a lesson learned from a lack of proper management. So what happened was that there was no limit really on fishing for capelin, and the capelin population collapsed. And what do you think feeds on capelin? Cod. Cod's a very valuable fish. And so when the capelin population collapsed, so did the cod. And people got very upset about this, and they said, we've got to do something about this. And what they did was create something that's called the capelin rule. And the capelin rule says that you must have a certain amount of capelin left in the Barents Sea, which they determined to be 200,000 tons at minimum must be left in the sea in order to have a healthy ecosystem, not just for capelin, but for cod. And the interesting thing here is that you've probably heard stories about cod populations being in trouble. Right here in the Northeast, the Gulf of Maine, the Georges Bank, all over the place, cod populations are in trouble. Many have collapsed. But right now, the Barents Sea has the healthiest cod population in the world. So from a bigger fisheries perspective, keeping capelin in the water has been instrumental in producing healthy cod populations. Okay, next slide. Okay, let's turn our sights to Peru for just a minute. The Peruvian anchovy has been fished for a very long time, but at relatively small levels until the early 1950s. And this slide that I'm showing is a slide of the population of birds, and they're often referred to as guano birds because these birds feed on forage fish such as anchovy and sardines, and their guano was very valuable and the product of a major industry which was used primarily to fertilize agricultural lands. And then people said, well, why should we wait for the birds to go out and eat the fish and produce the guano, and for us to harvest the guano? Why not go out and start fishing directly? And so this major industrial fishery for Peruvian anchovies started in the 1950s. And what you can see is that shortly after that fishery started, the guano birds, the abundance of the guano birds off of Peru really collapsed. And even though the anchovy fishery, the anchovies themselves have bounced back, the guano bird populations haven't yet really bounced back. And again, it's partly because of the life history of different kinds of organisms within an ecosystem. So forage fish live a few years, and they have the potential to recover quickly. But seabirds, marine mammals, big fish, these are longer-lived animals, and it can take quite a while for those species to make a comeback when their food source has been depleted. So in looking at this case study, the task force concluded that the Humboldt Current, which is the house basically for the Peruvian anchovy fishery, is currently very productive in terms of forage fish, in terms of anchovy, but it's an impoverished ecosystem when you look at all the other components of the ecosystem. Now here's another case where current management has moved towards establishing what we call a minimum biomass limit, a minimum amount of anchovy that need to be left in the sea to support other species within the ecosystem. Right now, the number that's being used is about 5 million tons of Peruvian anchovy should be left in the sea. I have to say that that's something that is undergoing investigation and may not stick, it may change. Okay, another study that our task force conducted was to look at seabird populations and the fish that they prey on around the world. And this diagram depicts the 14 different species of seabirds and where in the world those seabirds lived. And the idea was to see, is there a general pattern that we see when we look at seabirds and we look at the abundance of their prey? And in fact, we do. So I'm sorry to throw a graph at you, but let me try to explain it. So each one of these curves is for a particular species of bird. And on the x-axis, as you go from left to right, the prey abundance, or the species of fish that they prey upon, is increasing. And the seabird breeding success is increasing as you go from the bottom to the top of the y-axis. So what is this graph telling us? Well, okay, let's look at the right-hand part. What you see is a lot of curves that have flattened out. And what that means is that if there's enough prey, enough fish in the sea, these birds all do pretty well. They maintain stable populations. But there seems to be this critical threshold point, and if the forage fish falls below that level, then the seabird populations crash pretty precipitously. And the interesting thing was, when we looked at 14 populations of birds all around the world, the place where this threshold occurred from a stable population to a decreasing population occurred at a particular point, which was about 1/3 of the unfished prey abundance. And this paper was published late last year in the journal Science, and the title appropriately is 1/3 for the birds, Global Seabird Response to Forage Fish Depletion. So you can see we're learning a lot more about the importance of these fish, not just as fisheries, but their importance in the ecosystem at large. And the idea that our task force came to is that from a whole bunch of different points of view, it makes sense to establish not only a target for the fishery, but to establish something we call a minimum biomass threshold. That is, to leave a minimum amount of forage fish in the water, because as the forage fish go down in abundance, their predators follow them down that road. And in order to keep both the predator and the prey in good shape, there needs to be a point that we just don't allow the fisheries to go below, and fishing stops at that minimum biomass threshold. Okay, one of the big analyses that we did was to collect food web models. These are very complicated mathematical models. And when I say collect, I mean collect. We took published models that each had been developed by teams of investigators, and we pulled together all of these models because we wanted to see globally how do forage fish fit in to marine food webs, and what happens when you reduce their abundance in a marine food web to the rest of the ecosystem. So the little orange dots show where these models represented, And we collected them, and they had a lot of data. And I'm going to give you a brief synthesis of what we learned. So here's kind of a schematic of what one of these food web models might look like. And this is a simplified version, because it's only really showing the forage fish in the middle. And I've only included on this slide the species in this ecosystem that eat forage fish. And I'm only showing the one-way arrows of things that eat forage fish, whereas in a real food web, there are many different kinds of connections going in all different directions. But this is to try to simplify what we did. So first we looked at what is the ecological importance of forage fish in marine food webs. And one way to look at that is to see who eats them and how much of the diet of those things depends on them. So let's take an example. This actually is a food web for the northern Humboldt Current, which includes the Peruvian anchovy. So the species in here are the species in that system. In this particular ecosystem, 95% of the diet of seabirds consisted of forage fish. So think about it. If 95% of your diet consisted of these fish, do you think that you would be impacted by a change in forage fish level? You probably would be. Now, seabirds were extremely dependent on forage fish. Most other species were not. But interestingly to me, the second most dependent group of organisms on forage fish were other bigger fish. And many of these fish are commercially important fish. And they include things like tunas and mahi-mahi, dolphin fish, mackerel. 83% of the diet of these bigger commercially important fish depend on forage fish as food. And so on, here we go. So we took 72 models like this, and one of the questions that we asked of those models, combining the data all together, was how common is it to find predators that are highly dependent on forage fish, and what does that mean? And overall, we found that many predators are highly dependent on forage fish, and they include things like salmon and penguins and petrels and humpback whales. And we found that these species decline as forage fish decline. We also found that the more dependent a species was on forage fish as prey, the greater the response it shows. Now that seems like common sense, but it actually does come out in the data as well. And 29% of the ecosystems we looked at had at least one predator in the ecosystem for which 75% or more of its diet consisted of forage fish. And 75% of ecosystems, that means the vast majority of ecosystems out there in the world have at least one predator whose diet consists more than 50% of forage fish. So forage fish are really important, and having predators that are very dependent on them is really common. So we not only looked at the ecological importance, we also looked at the economic importance of forage fish. And very often in fisheries, people look at things like how many tons of anchovies are caught every year, how much do you get per pound or per ton of anchovy, and that is the way the value is recorded. Well, that's missing a big part of the story. The red arrow here is showing what was the value of forage fish when the forage fish are taken out of the water. But as we talked about before, forage fish are eaten by other commercially valuable fish. And there's a certain portion of each of these species production, and these are also the subject of different commercial fisheries. So what we did was to look at not just the direct value of forage fish, but their supportive value in supporting the production of other commercially important fisheries. And here's what we found. Here's the bottom line. That if you only look at the forage fish themselves, the direct value of their catch is about $5.6 billion a year. But if you look at their supportive value to other commercially important fisheries, it's twice as high. It's $11.3 billion per year. And the total commercial value of these forage fish we estimated to be about nearly $17 billion a year. So only looking at the value of the fish when you take it out of the water and not looking at this broader perspective really underestimates the total value, the economic value of these fish to the planet. And I know a gentleman who spoke yesterday showed a news clipping that said these fish are worth twice as much in the water as they are in a net. This is the study that, in fact, generated that kind of news coverage. And actually, we think it's true. So, in fact, let me just, before I go on to this slide, say that it's actually an underestimate of the overall value of forage fish because we only looked at commercially important fish. So think about this. If you're a recreational fisherman and you like to go sport fishing, the sport fish that you eat also depend on these fish as prey. And we didn't include recreational fisheries value. That's something that could be done later. But if you added that in, that would yet more add to the economic value of forage fish. And if you added in the value of ecotourism, people who go whale watching, people who like to go look at penguins or puffins, and put an economic value on those activities, again, the value of forage fish in a broader context would be even higher than the numbers shown here. Okay, so finally, the last big analysis that we did was we looked at different ways of managing forage fish, and this is the most complicated part of the analysis. I'm going to try to make it really simple. So we looked at many different strategies, but here we're comparing what I call conventional management of forage fish fisheries and then a more precautionary type of management, which was in fact the most precautionary of the many strategies that our task force looked at. And in a conventional fishing strategy, the target is to try to get the maximum sustained yield. Try to get the most you can out of the fish. In our precautionary scenario, we cut that value in half and we said, what would happen if we only took half as much fish, if we fished half as hard? And looking at this, what we call the minimum biomass threshold, I put down here that conventionally, there's guidance that about 20% of the fish population should be left in the sea. Now that's really kind of soft guidance. If you look at, for example, U.S. fisheries policy, that's not mandated. It's actually possible to fish a fish population down to near zero, and it would still be legal. But there are guidelines that say, if you get the fish population down to 20% of its unfished value, you really should back off. So it's kind of conventional, but it's not required. In a precautionary approach, we said, let's double the amount of fish that you need to leave in the water to 40%. Okay, what do the results say? What we found was that conventional management was very risky. And it was not only risky for the other species in the ecosystem, the penguins, the cod, the salmon, the tuna, but also for the forage fish themselves. Now remember, these are fish that live a short time, fluctuate in abundance, they are susceptible to environmental changes, and they have a susceptibility to collapse. And if you push them when they're down, if you hit a fish population when it's already down, then you can really do damage to those fisheries. So the red is conventional fishery management, and in the leftmost panel, what we saw were declines of the predators that depend on forage fish of about 30% in conventional management, whereas the precautionary strategy produced only an 11% change. Both of these fishing strategies reduced populations of predators, but one much more so than the other. But also we compared how likely was it that the forage fish population itself would decline during the course of the study, of this simulation study. And under conventional management, the forage fish actually would collapse 42% of the time. So that's not a very desirable result. And with precautionary management, the chance of a collapse of the forage fish population went down to only 6%. Now the total production, the yield of forage fish was quite different. So in this case, you can't get everything that you want. There are trade-offs. But if you want to have stable forage fish populations, and healthy predator populations, and overall a healthy ecosystem, then you need to be able to be willing to forego a little bit of yield, and that's what we've learned in this analysis. So what did we recommend? Again, the recommendations are very detailed, and they vary for different kinds of fisheries. But we did develop what we call a tiered approach, and this is an approach that says the more you know about a fishery, then the harder you can fish. It's safe to go a little bit, to fish a little bit harder when you know more. And when you know very little, then you really should not. We recommend focusing on predators. And for typical fisheries that today are considered to be well managed from a single species point of view, our recommendations say that the amount of fishing for forage fish should be cut in half, and that twice as much fish should be left in the ocean. Again, this is for what are today considered to be well-managed fisheries. This is not a good sign for the future supply of forage fish to the market if these recommendations are followed. And we also say that it's not enough to just control the numbers. We need to look at spatial and temporal management. So in conclusion, in the world of fishery science, the world of fishery sustainability, things are changing. And one of the ways that they're changing is that we're going away from the idea of managing one species at a time without considering the fact that it needs a home, that it eats and competes with other fish, that other organisms feed on it. And so we're going towards what we call a more holistic ecosystem-based approach. And the kinds of analyses that I've done here are being done for all kinds of fish and for all kinds of questions. Even though these recommendations may not sound like good news to you, there are some benefits of taking this approach, and here are just a few. They maintain the ecological roles and services that forage fish provide. It reduces the risk of a forage fish fishery collapse, which is good if you want to maintain a steady supply of product. And it may increase overall the value of commercially valuable fish around the globe. And with that, I will say thank you, and thanks very much for your attention.